Hi everybody. This video is to help you calculate the energy that your solar system is able to capture over the course of the day. This can be a little bit of a tricky calculation, so we're going to run through a couple of basic ideas and then show you exactly with an example how you would solve for the energy captured by your system. Let's begin. Let's talk about the strange unit that we use for energy. You may remember earlier in the year when we talked about energy. Specifically, we talked about the work being equal to the force times the distance. When we spoke about this earlier in the year, we mentioned that this energy measurement of energy or work is measured in what we call joules. But joules are a very, very tiny unit of energy. For example, a candle would use about 1 joule per second, or sometimes we think of this as 1 watt, right? A watt is how quickly we're using energy, right? So a candle can use about 1 joule of energy each second. This isn't very convenient for us in the modern world because we use a lot more energy than this for things like our computers and for air conditioners and everything else. So a more convenient unit, although strange unit, is to think in terms of how long I've used a wattage for. Now, if you don't remember, wattage is a measurement of what we call power. And power is just the rate at which we're doing work. It is the work we do per unit of time. So another way of writing down the work I do, right, I could write down that the work is just equal to the power multiplied by the time. And this explains the strange unit of energy used pretty much on all electrical bills and, if you ever actually go to build power, a solar paneling system on your house someday down the line, they use something called a kilowatt hour. And let's talk about this real brief so you understand how it's connected to the idea of joules and work. You see, kilowatt, right? This is a measurement of power, right? Watts, kilowatts, power. And hours, right? Hours, well, that's just the measurement of time, right? So this is for time, right? Hours are time, and power is kilowatts. So we can express energy by just a multiplication of a wattage times time. And these are average values, but can be used to calculate real amounts of energy. And we can show how this is connected to joules. A kilowatt stands for 1,000 watts times 1 hour. Now an hour is the same thing as saying 60 seconds multiplied by 60 minutes. If you multiply 60 seconds per minute times 60 minutes per hour, your minutes would cancel out, and you're left with 3,600 seconds. This is equivalent to, this is the same thing as 1 hour. So, to figure this out, right, we multiply the amount of watts, 1,000 in this case, times the time, 3,600 seconds, and we find that 1 kilowatt hour, sometimes you write it as k-watt hour, is equal to 3,600,000 joules. Remember that watts are the same thing as joules per second, so the seconds would cancel out, and you're left with joules. So this explains how a kilowatt hour is the same thing essentially as saying in joules. It's just a different unit of measurement. It's like using gallons or cups, right? They're similar units. They're just used for different things. Now to work it out for our solar panel, well, what are the things we need to know? How do we actually work out the amount of energy, the kilowatt hours we gather during a day? That's a little kind of tricky, right? So basically, we have a roof, right? And the roof is going to have little panels on it. Let's say in this case I have a system that's got 4 panels on it, right? And the sun is going to shine down, and it's going to deliver energy to the surface of the roof and the solar panels. And we can use this energy from the sun and see how much of this sun energy is captured by these panels. One thing we need for this is something called insolation. Now, insolation is a tricky thing. Usually it's measured by the amount of energy a single square, right? A single square. So if we had, let's say, a square, this is 1 meter, right? So insolation is a measurement of the amount of energy captured by a single square over a certain period of time. And we do this over a period of time because during the course of the day, the amount of energy hitting the roof changes, right? Early in the day, not so much. When it's close to noon, there's a lot more energy available, and then at the end of the day, a lot less energy available. So insolation is a way of sort of averaging it out for the entire day, right? In the case here, what has been given in the project is that the insolation is 6 kilowatt hours per meter squared, right? That's the amount of energy each day. And what this says is if I had a single square that was 1 meter by 1 meter, and I let it sit on this roof for the whole 8-hour day, it would gather up 6 kilowatt hours. This allows us to simplify the amount of work we need to do to figure out the total energy our system is producing, because essentially all we really need to know is how many squares we have, right? If I know one square gives me 6, if I had 2 squares it would be 12, 3 squares would be 18, and so on and so forth. So step one is we have to figure out how many squares do we have on the surface of our roof, right? We call this area, which I'm sure you're probably familiar with. Um, in this particular example, they give us, I'm going to say we have 4 panels, right? 1, 2, 3, 4. You probably have more than 4, but for this case, I'm going to use 4 as a simple kind of example to show, right? Now to do this, basically we just need to figure out what is the area covered by these 4 panels. So first we need to know how much is the area in one panel, right? Now from the sheet, right, the sheet tells us that the area, they don't tell us the area, but they give us enough information to figure out the area. They tell us the width, the top part of this panel, is 992 millimeters. 992 millimeters. And they tell us the height of the panel is for the first, this was specifically for the 60 cell panel. They're a little different, both of them, but you can look up whichever one you used on your roof, or both, depending. For the 60 cell panel, it has a height of 1,640 millimeters. 1,640 millimeters. So then we have a length, right? And we got the width, and so we could find the area. One thing we should do first, though, is that this unit is in meters squared, and these measurements are in millimeters. So we are going to need to do a quick conversion. I know that 1 meter is equal to 1,000 millimeters. So if I want to convert this to meters, this would be 1.64 meters. That's the vertical side of my single panel. And this top part's going to be 0.992 meters. That's the horizontal part of my panel. And now, knowing the length and the width, we can calculate the area for a single panel. You should all be fairly familiar that the area for a rectangle is just going to be equal to the base times the height. In this case, the base of this one we're going to use is 0.992 meters. And I'm going to multiply that by the height of 1,640, well, specifically for meters, 1.64 meters. Remember, we want to have the same unit for both to get squares, right? So I put this in my calculator, and we find that the total area of this particular panel, 0.992 multiplied by 1.64. That's going to give us an area that is 1.6. I'll use 3 digits since we use 3 digits up here. 1.63 meter times meter gives me meters squared. This is the area for one panel. And now I know the area for a single panel. I could find the total area covered by the total system because I know I have 4 panels, right? 1, 2, 3, 4. So to find for 4 panels is going to be equal to the area for one panel, 1.63 meters squared, multiplied by 4 for 4 panels. And remember, this is for the area, right? One panel area. Throwing this in my calculator, I can figure out the total squares covered by my system. 1.63 times 4 gives me 6.51. So the total area, surface area, is going to be equal to 6.52 meters squared. That's the total number of squares that my solar system is going to cover. Now, knowing the total number of squares that the system is covering, and knowing the amount of energy one square could collect in a day, which is 6, right? All I got to do is multiply the amount of energy one square would get in a day times how many squares I have. So the total energy, right? Total energy from the sun is just going to be equal to the area, surface area, multiplied by the insolation. So in this case, the surface area is 6.52 meters squared. And I'm going to multiply that by the total insolation for one day, which is just going to be equal to 6 kilowatt hours per meters squared. And you can see now, because the meters are in the numerator and meters are in the denominator, they're going to cancel out. And this would give me a total amount of energy absorbed by the sun. It's just going to be 6 times 6.54. This gives me 39.12 kilowatt hours. Now this is a lot of energy. In fact, this could cover pretty much everything that your household would do for a day, and this would be great. We could power everything with solar panels. But unfortunately, we don't actually capture all of this energy. This is just the amount of energy that the sun is putting down onto the surface. So the last piece of the puzzle to figure out the amount of energy I actually get to keep, useful energy, is I've got to remember that these panels only capture a chunk of the energy. It's something called the efficiency of the panel. Now, for this particular panel, for the 60 cell panel, right, 60 cells, its efficiency is only about 19%, meaning it can only capture 19% of the total amount of energy coming in from the sun. So to work it out, the energy actually captured that's just equal to the total energy from the sun, multiplied by the efficiency of the panel. Fairly straightforward in this case. The total energy that was hitting the panel we figured out in the previous calculation, multiple 39.12 kilowatt hours. And I multiplied this amount by the amount of energy I actually am able to capture, which is only a chunk, 19%, right? But we're going to write that as a decimal to multiply it. So that's the same thing. 19% is the same thing as 0.9. 0.19 is the same thing as 19%. We multiply the two things together times 0.19. And we find out of all that energy that came down on our paneling, our four panel system, we only capture 7.43 kilowatt hours of energy. I hope that was helpful. A little quick recap. Step one, figure out the total the area for a single panel. It's pretty straightforward. Length times width. Make sure you got your units correct. Step two, work out the total area based on how many panels your system has. You can find the total area. And then not lastly, but then the next step is you're going to multiply this total surface area times the amount of energy the sun is delivering on each square. In this case, 6. It's the same for everybody, times the surface area. And then once you've got that final total energy from the sun, you figure out the amount that actually gets kept by the panel using the efficiency. You multiply the total energy from the sun times the efficiency, and you get the energy captured by your system. And there you go. That's everything you need.